Pleasure to introduce Efstathios Charalampidis, or for his friends and colleagues, Stathis. He's our new recruit in the math department. He's also part of the Nonlinear Dynamical Systems group. So Stathis comes from a path all the way back from Greece, where he studied physics, some funky stuff about relativity. Then he started, relativity, it's a lot of math, so he started switching more and more into math. He did a visiting assistant professor for 3 years in Amherst, Amherst. And then he was a faculty at Cal Poly San Luis Obispo for 4 years, 5 years, 5 years. And he decided to go to greener pastures, and now he joined us. And I think Stathis is a little bit like me. We go to the same shrink. We have a tripolar disorder. We do not know if we are applied mathematicians, physicists, or computational science persons. So I think the talk that he's going to give is going to give you kind of these super nice mix of math, computation, and physics all together in a nice box. So thank you very much, Stathis.
Thank you very much, Ricardo. Thank you very much for the introduction. Thank you, Jose, for running all this beautiful seminar series. Thank you all for coming today. This is a journey that I think started over 10 years ago with different topics, primarily focused on physics. But what I have experienced all these years is that what is really important is that having a little bit of background in physics and the tools that you need to solve the equations that model those phenomena, you can do a lot of interesting stuff. So that is something that, as a message to students that are here. So the problems that I'm interested in are problems that involve wave phenomena. So we're going to spend some time at the very beginning of this talk about wave phenomena. The ones that I'm very much interested in, those can appear in many contexts in physics, from in order waves, in optics, in atomic physics. Those phenomena are governed by some fundamental equations, so that's the third part of my introduction, that we're going to see those fundamental equations. And in fact, there is something quite interesting about them, is that some of them can be solved explicitly, namely on a piece of paper, because they enjoy a property that we call it integrability. But let's keep it simple, that there are some problems that you can solve them analytically, even nonlinear problems, but some others we cannot do anything other than approximating solutions to these models. So that brings forth computation, and in particular, in the second part of my talk, we're going to see some techniques emanating from fixed point methods, namely Newton's method, and how we can use Newton's method in order to do something more than just finding a solution, but finding branches of solutions. And that will be the beginning of what we're going to call as numerical continuation technique. So you have a parameter in your problem, you want to vary this parameter, you're going to find whether such solutions exist for that parameter. So that is an algorithmic way, if I may, to trace branches of such solutions. Then quite recently, well, not recently, but years ago, when I was in Amherst, with colleagues at Oxford and with my postdoctoral mentor at UMass, Panos Kovridis, we have employed a method that can actually factor out solutions in your problem. It's essentially a penalization method that allows you to find multiple solutions to a given nonlinear PDE, or a system of nonlinear equations, if you may. That will be the deflation method, or coupled with continuation method, that gives birth to the deflated continuation method. So having laid down the background of what are the problems that I'm interested in, some basic methods, then we're going to see families of solutions in different models that are coming from atomic physics. Those wave-like phenomena there correspond to matter waves in a very funky name, nonlinear Schrödinger systems. If you have ever done quantum mechanics, you may have heard of Erwin Schrödinger. That's a model that it is nonlinear because there is something else going on there. You have interaction between subatomic particles there that gives birth to a nonlinear problem. We're going to use deflation in order to see whether we can find more solutions to type problems, but also use continuation methods in order to study rogue waves, those waves that we're going to call them extreme events, waves that come out of nowhere and disappear without a trace. They have a large amplitude, and specifically in setups where they're coming from optics, those are modeled by lattice equations. And we're going to see that with the use of such methods, we can actually find some quite interesting solutions to those problems. And lastly, which is part of my direction funded by the National Science Foundation, it's about the study of collapse solutions. So essentially, if you have initial data in your problem, you just evolve them forward in time. You want to see whether those solutions are going to blow up, are going to lead to regular solutions. If they blow up, what does this mean? So this is a study of what we call a self-similar collapse. And the model that I'm going to use is the nonlinear Schrödinger equation, because it's kind of a universal equation that can work in many contexts, in water waves, in optics, in atomic physics, and so on. And then, if I have time, I will summarize some future directions and research opportunities for students. Okay? So, wave-like phenomena, we are talking about disturbances that propagate over space and time. If you're sitting on a rainy day, which is quite unusual in San Diego, sitting next to a pond where you see falling raindrops on a pond, you just see the formation of a droplet that actually propagates over space-time. We're quite fortunate enough to live next to the ocean, where if wind blows the surface of the ocean, we generate ocean waves, which is a quite interesting object for surfers. But also such type of disturbances, such type of waves appear at the macroscopic scale. Namely, if you have a system of two binary stars, they disturb the fabric of space-time, generating gravitational waves predicted by Einstein 100 years ago, and they have been detected experimentally in 2015. Also, at the microscopic level, a light beam, when it encounters an obstacle, it undergoes what we call as diffraction. So that beam gets split into different colors, different wavelengths. Okay? And also, we have this very beautiful property, which is called the wave particle duality in quantum mechanics, that subatomic particles can behave as particles, but also as waves. So that was actually the principal vehicle for the development of quantum mechanics. Okay? So the other type of waves that I'm interested in are those rogue waves, those gigantic waves that have an extreme amplitude. They can appear out of nowhere and disappear without a trace. Here's an example that I picked by Matthew Rivrin. This is essentially out of a sudden, you have the formation of such a big hump of a wave that could be quite disastrous. Here is actually a lighthouse, but if you think of it as an oil rig, such formation of such extreme waves can be actually quite catastrophic for the environment. So it is quite important to understand under what conditions such waves can be actually generated. Okay. Now, at the level of optics, people have started actually realizing nonlinear waves in general, and specifically in optics. What happens is that when you have the propagation of a wave, you are competing between two forces. One is dispersion, or diffraction, if I may, which tends to spread things out. And then you have nonlinearity, especially if you propagate through an optical medium. So as soon as those two forces are balanced each other, then you can actually form a solitary wave, a coherent structure that can propagate, in fact, undistorted in nonlinear dispersive media. So back in the 80s, there were experiments about such waves in optics, where if you just increase the power of an incident beam, then you can actually form a nice solitary wave. But if you actually increase the power of that wave, it can actually undergo collapse. Essentially, it starts increasing its amplitude. Such type of waves have lots of applications in telecommunications in particular, and people 7 years ago, for example, I picked an example where they can generate a soliton burst, essentially a group of such waves that can actually be used to transfer information in an optical waveguide, for example. However, as people have noticed back in the 80s about collapse, about waves that can actually have essentially an infinite amplitude and the very small width, though such type of waves can be in fact quite useful, especially in the so-called, I think it's called LiDAR. It's the light detection process where they can actually send such a beam that will undergo collapse. Collapse is arrested by ionization of the atmosphere, and they can actually measure pollutants in the atmosphere through backscattering. So that is a quite important thing. But also such type of collapsing events or filaments, if I may, can be used also for neuromorphic computing, essentially mimicking how our brain works by establishing synapses between neurons through the propagation of filaments. That's not only the applications that we can think of. There are other applications in atomic physics where the fifth state of matter, as is called, the Bose-Einstein condensation, that state of matter was predicted by Bose and Einstein, where when you take a gas and you cool it down to almost 0 Kelvin, everything actually dances together. It becomes a coherent pulse, and it was observed in the 1995. Here is, in fact, a picture about the two experimental groups involved in this direction, one at the Joint Institute of Laboratory Astrophysics and the other one at MIT, where as you keep increasing the temperature, then everything condenses. So you can think of this as a localized pulse or as a solitary wave. Now, with all this said, those solitary waves, remember that it is the balance between nonlinear effects and dispersion. One of the first nonlinear equations that has behind that, it has a very beautiful story back in the, I think in the 1800s. But for us, the first nonlinear problem in the context of water waves, it is the well-known Korteweg-de Vries equation. You have a third-order dispersion term, a nonlinear term, a quadratic nonlinearity. It has a lot of application in water waves. And quite surprisingly, you have a nonlinear problem, and that nonlinear problem has a solution, which is the Soliton solution. It is a traveling wave that can actually travel without changing its shape, as is shown here, with a speed c. And it describes the high displacement of the water surface from its equilibrium. Now, this problem, just maybe one or two words. The KdV, as is known, is an integrable model, meaning that it has an infinite number of conserved quantities, or equivalently, you can write down a system of two linear equations whose compatibility condition gives birth to this nonlinear problem. So if you study that linear problem, the eigenvalues will give you the Soliton solutions that you have. So a couple of conserved quantities are shown here. It conserves the mass, the momentum, and the energy. By conservation, I mean that those quantities are conserved in time. Okay. So for the other end, the nonlinear Schrödinger equation, which is kind of a universal model appearing in optics, in water waves, and Bose-Einstein condensates. It's also an integrable equation. It has a nonlinear term. If you have ever seen the linear Schrödinger equation in free space, you will recognize the left-hand side and also the second-order dispersion term. That nonlinearity comes from the interatomic interaction in that cloud of atoms. So the thing here is that you have a complex valued solution. In fact, that doesn't have any meaning. And I think when Schrödinger wrote down the linear Schrödinger equation, it didn't make sense to him until Max Born said, well, your equation actually might have a meaning if you consider probability density. So essentially what you measure is the mod psi squared, which tells you the probability of finding a subatomic particle at position x and time t. Okay. However, the nonlinear version of that, which is coming from atomic physics and optics, is integrable. It has explicit Soliton solution. Depending on what prefactor you use here, gamma can take the values plus and minus 1. Now, if you think of this in terms of Bose-Einstein condensates, that when gamma equals -1, then you have essentially attractive interactions between your atoms. If gamma is positive, then you have repulsive interactions. Regardless, you have two explicit solutions at the respective cases. You have the bright Soliton solution. If you think of this again in terms of probability densities, the mod psi square, if you measure that, essentially wherever you are non-zero, that means that you are more probable to find those particles at that position. The other case, when gamma equals +1, this is what we call as the gray Soliton solution. In fact, it is a traveling wave solution. You can actually appear here or there, but as I keep decreasing, I think B, which actually controls the velocity of this thing, that dip is going to actually coincide at the origin. and that is called the dark soliton solution. So that solution has a dark spot in the middle. Okay. So that's not only the case with the NLS, because I'm going to use that acronym, the NLS. It also has other types of solutions when you have attractive interactions, when gamma equals -1. So if I can think of a rogue wave essentially sits on a finite background, if you think about the surface of the ocean, and then you have this high peak that will appear out of nowhere. So in fact, since the model is integrable, you may have more than one explicit solution. So one extra solution here is one that is parameterized by this parameter alpha, and depending on that value of alpha that you have, if you graph the mod psi or the amplitude of your solution, you're going to see that the solutions anyway sit on a finite background, but depending on the value of alpha, you have a different localization. So you have a spatially periodic solution, periodic in X. At alpha equals 0.5, you have this isolated pulse, which mimics essentially a rogue wave. And then when alpha is greater than 0.5, you have a time periodic solution. In that context, when alpha is less than 0.5, it's called the Akhmediev breather. Alpha equals 0.5 is the peregrine soliton. And when alpha is greater than 0.5 is the Kuznetsov-Ma soliton. Here is essentially a spatiotemporal evolution of the solution. I'm just plotting the amplitude of that. So as you can see, if you start with t equals -4, you have nothing, and then at t equals 0, you have the formation of this pulse, and then nothing. So it appears out of nowhere, and then it disappears without a trace. Okay. So it is not only the continuum model, continuous models, meaning continuous in X in your spatial variable, but you can also consider discrete variants of those models. And if you have taken a class in numerical analysis and you have played a little bit with finite differences, you may actually recognize that this term in the first term in the right-hand side, that kind of mimics the second-order accurate central finite difference formula for the second derivative. However, h here is equal to 1. So this is a pure discrete model. Okay, it has quite a lot of applications in optics. People actually use this model to compare theory and experiments. However, it has some drawbacks, and chiefly, this model is not integrable in the sense that you cannot write down an infinite number of conserved quantities. However, with the logic back in the 70s, they just slightly modified the NLS, and they show that instead of having this nonlinear term, essentially the mod psi n squared times psi n, if you take the average between nearest neighbors, then that model, they show that it is integrable. And if you think about it, if you just introduce the h term here and you start decreasing h, then that average essentially is going to coincide to the psi, right? If you just average nearest neighbor. So that model is integrable. It has the discrete analog of the peregrine soliton as the continuum limit. It also has this time periodic solution, this Kuznetsov-Ma breather. Here is the discrete, essentially a snapshot of this rogue wave at the discrete real. And here is this spatiotemporal evolution of this time periodic orbit or this Kuznetsov-Ma breather. Okay. However, those are the cases where you have something that comes from integrability. In other cases, when you cannot get solutions analytically, there are specific models that actually are not integrable. So specifically, the NLS, but now if I just change the nonlinear term, I have a different power, sigma. I can have the NLS now in higher dimensions, but also including an external potential, which is quite useful while conducting experiments. You want to confine the atoms in a specific region in space. So experimentalists consider external potentials there. So that model now becomes non-integrable. The DNLS that we already encountered, but also there is the KDV, but now the generalized version of it, not when P is not equal to 2, essentially. So what can we do instead if we want to see whether such models have solutions? Well, if you're dealing with a continuous model, such as the Gross-Pitaevsky equation or the GP, you can think of this as the NLS plus an external potential V. You have to tell the computer how to solve this problem. And how you do that, you just discretize your space, you pose it on the computer, you use your favorite approximation in space, finite elements, finite differences, spectral methods, and so on. But at the very end, what you get a system of nonlinear equations, coupled ones, okay? So those nonlinear equations are cast into this form, so you have a root finding problem, okay? And how you solve this efficiently? Well, you have Newton's method available, which enjoys some beautiful properties, including quadratic convergence close to the solution itself. But in fact, when you use Newton's method, maybe I should write this. So in this case, when you write Newton's method, you have xk minus, essentially you have what we call the Jacobian, essentially, or the Frechet derivative, fxk. So essentially you have to invert typically very large metrics, which is quite expensive computationally, but instead what you do is that you observe that this is the action of a matrix to a vector. I can actually think of this as a vector, I mean the action of this inverse to my nonlinear residual. And then if I multiply both sides with j, I'm going to get rid of this j inverse. So essentially what I'm going to get my Jacobian times the correction in Newton's method equals to something that you know. So that is essentially a system of linear equations. Or in other words, if you want to solve a nonlinear problem, it's all about solving a linear problem. Okay? So then you do this repeatedly until you converge. That's about the existence of solutions here, but also you want to see whether those solutions are stable. So essentially, if you work on a model that has applications in physics and engineering, you ask the question, well, is this solution observable? I mean, if I conduct an experiment, am I going to see this? The answer is coming from what we call as linear stability analysis. So essentially, you're studying how a perturbation to the solution will affect the solution. So that, all in all, gives you an eigenvalue problem that typically has this form. So you have an operator acting on an eigenvector equals to an eigenvalue that will tell you whether you are unstable or stable. And then combined with numerical continuation. So typically all those problems involve a parameter. For example, the NLS has sigma, the JKDV has P. We'll see that the gross Pitaevsky will have another parameter which is related to the number of atoms that you have in the condensate. So you want to see how the stability changes as I vary my parameter. So that is part of what we call as bifurcation analysis. So a little bit about numerical continuation. So when you have a problem that involves a parameter, so just for simplicity, I'm going to call it lambda. I want to see whether this problem has solutions as I vary this lambda. So one of the easiest approach that we can use is what we call as a natural continuation. So suppose that you know something about your problem, lambda naught, I have an initial guess x0, then in order to find a solution for a nearby value of lambda, I'm going to call it lambda 1. What I'm going to do is that I need to feed my nonlinear solver. I should have mentioned that in Newton's method, you have to start with what we call as an initial guess. So when k equals 0, you have to supply the method with something, and then iteratively is going to find the solution. So suppose that you have this information, you just change your parameter lambda 1, and in order to feed a guess to your solver for that value of lambda 1, essentially what you do is that first you have to find this prediction for that value of lambda 1. So you move along the tangent direction of this curve, and then you fit this to your Newton's method, and then you converge to that point. Then you do this in a sequential manner, and you can actually trace an entire branch of solutions. However, this method is going to fail when you encounter a turning point. So when you have a bifurcation curve, so that is essentially monitoring the norm of my solution as a function of lambda. So when your bifurcation curve somehow has a turning point. So here, at that turning point, Newton's method is not going to convert at all, because the Jacobian becomes non-invertible, so there is nothing else to do. However, if you reparameterize your problem in terms of the arc length, essentially instead of varying your lambda, if you vary the arc length, geometrically speaking, I'm not going to jump into the equations, but what happens is that I have my bifurcation curve. So here I'm just cheating, saying that I know how this will look like. So what you're doing in this context, in the pseudo arc length business, is that you're trying to find the point of intersection of your bifurcation curve and the plane that actually intersects that curve. So essentially, instead of solving the f of x equals to 0, you're trying to find the point of intersection of this guy and that equation, which is essentially the equation of that plane that I'm talking about, okay? It's a normal vector essentially specified by this x naught dot lambda naught dot. And the dots are derivatives with respect to s, okay? So this way you can actually bypass turning points. And as an example, if I have just a scalar equation, one unknown, lambda is my parameter, I can use this continuation method, I can trace a branch of solutions, but if you're curious enough, as I am, I'm asking myself, do I have more solutions to this problem? If you're brave enough, maybe as not I am, you can actually start picking other guesses. You can actually vary your lambda and you can find another solution. So then you can use pseudo arc length continuation method, and then you can find another branch. However, what is the importance here is that your problem may have actually more than two disconnected branches of solutions. And how can you trace those branches? Well, now this is the point where we're going to see deflation, which is combined with, if you combine it with numerical continuation, you construct this deflated continuation method. So besides this jargon, what does this mean? It means that you fix your parameter lambda, you solve your finding problem for a given initial guess, you find x1. You raise the question where this problem may have more solutions. In order to do that, you no longer solve f of x equals to 0, but instead you solve the problem m times f equals 0, or g of x equals to 0, where m is this operator. Okay? So what does this operator do? You have, in the first term, you have some sort of a repulsive potential. It is like 1 over the norm of x minus y to some power p. And what happens is that if Newton's method is very close, note that here you have the x1. So the x1 is the one that you found. If you're very close to x1, this term actually will push Newton's method away from this point x1. So you're not going to, there's no way that you're going to approach that point. However, there is the danger that you may actually go quite far. And if you don't have this term here, if you're quite far, that means that you're going to be 1 over something very large, so essentially 0 times f, it will give you 0. So Newton's method may erroneously converge to something that is not a solution to your problem. So that's why you have this shifting term sigma. So this operator enjoys some these nice properties, namely that if it converges, if the g of x converges to a solution that is a distinct solution, okay, it does preserve the set of solutions that you already have found for that fixed parameter value of lambda, and then you can actually proceed recursively. You can keep applying this deflation operator as many times as more solutions you find, okay? Then, if no convergence happens, then you just say, I'm done for this value of lambda, and then I'm going to start seeking for solutions at the nearby values of lambda. So how does this apply? If I pick this problem again, I'm going to start with x naught equals minus 0.1. I'm fixing my lambda. So essentially, since I'm close to this point, Newton's method is going to converge here. Okay? You deflate now the solution, meaning that you pre-multiply your nonlinear residual with this m for that root. You're going to converge to that. You pre-multiply now your m with another m for that solution. Since there is nothing above it, you say, I'm done. I'm going to start moving towards other values of lambda. So we can now start tracing solutions as you increase lambda. You're going to find, again, those two. There is nothing above it for that value of lambda. And at some point, you're going to actually be able to get the other solution that it is on the other branch. So then you can keep tracing. That's, you can actually find another branch in your problem. Okay? So that is quite interesting because you can actually do, in, as we say in dynamical systems, we can study bifurcations. Here is an example of a pitchfork bifurcation, namely that your solution is stable for a certain interval of your parameter. Then at lambda equals 0, the parent branch becomes unstable, but it gives birth to two stable branches. So that looks like a pitchfork. Okay? So with that method, we can study now one of the problems that I worked on, the study of matter waves in the context of atomic physics. Essentially, I have now a non-integrable model. I have an external potential. If you have ever seen this functional form, that is what we call the potential of the quantum harmonic oscillator. As omega is the, we call it as is the frequency of that potential. It is a trap, essentially, because it confines the atom in a specific region in space. If I want to look now for stationary solutions, essentially standing waves, my problem is self-adjoint. I can actually use the method of separation of variables. Now mu is the separation of variables constant, is my chemical potential. If I do my algebra, I'm going to get a steady state problem. So here is my parameter mu. And now the question is, how can I solve this nonlinear problem? Well, you have to use Newton's method or variant, but you really need a good initial guess. The good initial guess is coming from the following, that if you disregard your nonlinear term, and that comes from the fact that when in your condensate, in this collection of atoms, the number of atoms is actually quite small, meaning that they do not interact, I can actually disregard this nonlinear term, which is responsible for that interaction. So what I get the quantum harmonic oscillator problem, a Sturm-Liouville problem that I have to solve for mu and psi. So that will give me essentially the value of mu and the associated eigenvector psi that I can use in my Newton's method in order to start now increasing mu, or the number of atoms, such that this term now becomes important. Okay? Now, the next question is about the stability. So how can I study the stability? How can I study the response of the solutions under a perturbation? So you assume a perturbation of this form where your epsilon here is the small parameter. You essentially linearize your original equation around that stationary solution, and what you get an eigenvalue problem. Okay? So that will tell you something about the stability or instability of the solutions. Just a remark is that if your eigenvalues, if you have an eigenvalue that has a positive real part, here, due to this exponential term, this term is going to increase over time. So that tells you that your solution is unstable, as a first remark. However, lambdas can be also complex. If lambda is complex and it has a positive real part, what's going to happen? We know from Euler's formula that's going to be e to the lambda r times t plus I times lambda r times t. So you're going to have essentially a growing amplitude of this term and oscillations. Okay, so that is what we call as an oscillatory instability. So in summary, what we did with this method is that we benchmarked it against known results. So you pick the ground state that comes from that inner limit, as we call it. So we solve the Sturm-Liouville problem. We have the initial guess. We use that in Newton's method, and now we vary the mu over very large values of mu. So what happens is that when you vary mu, essentially you keep pumping atoms in your condensate, so you become fatter and fatter. Then, as soon as you have reached this value of mu, you use deflation, you get a second solution. You deflate those two, you get a third. You deflate those three, you get a fourth, and so on. Okay? So here, what you have is that, and then as soon as you do that, then you just lower mu in order to see where those solutions are coming from. You want to classify them and see where those solutions are coming from. And in fact, what you find is that besides the ground state, the first excited state, it comes in two flavors. One is that it has a stripe. By the way, in those panels, I'm graphing the density of the solution, or the probability density, if you like, as a function of x and y. It's a 2D problem here. It comes in two flavors. You have a stripe along the x direction, and this solution is what we call as a vortex solution. So what happens is that the vortex solution, I can actually increase mu until it gets fatter and fatter. This solution, however, there is something that happens here that gives birth to another branch, this one that essentially involves two vortices, and the very same branch later on, something else happens here that gives birth to a solution that has three vortices. So those are examples of what we have seen before, bifurcation. So those are Pittsburgh bifurcations. My comment here is that wherever this is solid blue, this is a stable solution. So an example of how the spectrum or the eigenvalues look like, all of them are aligned on the y-axis. If you have now a pair of eigenvalues, one having a positive real part, but those are purely real, that means that you actually deviate from your equilibrium in an exponential fashion. So that was the case with this branch. So as you see, the parent branch, this solution was stable, then it became unstable, it became red, and the daughter branch is stable. So that is an example of a pitchfork bifurcation, okay? And then you can have oscillatory and unstable solutions where you have complex eigenvalues, they appear as quartets, which is associated with something else in the model. It has to do that it is Hamiltonian. It has a positive real part, and essentially that highlights the emergence of oscillations with a growing amplitude. Okay. Now, besides this, as soon as we benchmark all those results, we found in total 63 solutions in this problem, including 15 new ones that have never been reported in the literature. This is a subset of some of the solutions that we found. And with this finding, we started getting excited and we considered higher dimensions than 2. So in fact, before moving to that, actually, I have to make a comment, is that when you study the stability of this problem, essentially when you solve this eigenvalue problem here, oops, okay, when you solve this eigenvalue problem here, that looks quite innocent, but in fact, sometimes it's not, because you have ever heard of what we call as condition number of a matrix. If the condition number is very large, it is a metric that tells you how sensitive your calculations are to round of errors. In most of the cases, this matrix is quite sensitive to round of errors, and when I was computing those eigenvalues at the two-component problem in particular, I was getting an absolute mess. Okay, so those are the imaginary and real parts of the eigenvalues as a function of my continuation parameter. So something that I keep telling my students is that when you solve a problem numerically, make sure that you plug it back to the equation that you solve and see whether you satisfy the problem. And when I did that, I just got a relative error. I picked one eigenvector, one eigenvalue, and I found that in my L1 norm, I have a completely garbage result. Okay, this is absolutely garbage. And the problem was that the lack of accuracy here, and I went a little bit crazy thanks to Hans Johnston. He's a faculty member at UMass who actually pointed me towards a package that you can do extended precision calculations. It is a package that is called MP-EIGS. It's a commercial one. You can in MATLAB in particular. And when I did those calculations, 34 digits accuracy, 34 digits representation of the numbers, I got a fairly accurate result when I computed those relative errors. But just to get this result that I'm showing you, it took 3 months. And I had the thing something like 40 branches. Okay, I wouldn't have been here. So, quite likely, next department at UMass, at the computer science department, there is a guy still named Eric Polizzi, who has developed an eigenvalue solver named FEAST, which can find eigenvalues inside the contour on the complex plane. And in order to get this computation done, it took something like 20 minutes. So that was a huge improvement. And by the way, the comparison is very well. So anyways, that was just a comment that make sure that if you solve problems numerically, just double check and see what else you can do. So we got really excited about this direction, and we started actually considering higher dimensions, applying essentially deflation to higher dimensions. And indeed, in the Gross-Pitagoric equation, in that model that I showed you in 3D now, we found some quite interesting solutions besides the known ones. This is called the planar dark soliton with a vortex line. You have 2 vortex lines, vortex line stars, 4 vortex lines, and so on. Those solutions actually are brand new. We have found them using deflation, and that was quite interesting for us to see, and especially their stability. But what happens is that most of those solutions are unstable or weakly unstable. On top of that, we found a bifurcation that comes from the planar dark soliton. It's coming somewhere here, which was quite cool, actually. Another applicability of such type of continuation methods actually is with a project with Ricardo a couple of years ago, where we use pseudo arc length continuation in order to find solutions in a three-component Gross-Pitevsky system in 3D, quite challenging computationally, and we found two branches of what we call as path random vortices, or two Alice ring solutions, that we were able to trace them using pseudo arc length continuation method. As you see, you have a turning point, and then you can actually pass that by using a reparametrization of your bifurcation curve. Okay, so switching gears. So how much time I have? Almost 10 minutes max. 10 minutes max. Okay, so switching gears now, when we're dealing with discrete models, one of the problems that I have been interested in is the formation of Rho waves in discrete systems. Okay, so if you recall the Peregrine-Shorten, which resembles such a wave that comes out of nowhere and disappears without a trace, I can think of it as a time periodic solution, but with period going to infinity. So instead of finding that solution, I can actually take limits, or I can find essentially a time periodic solution with period t, and then I can actually play with that period t and see how can I approach that limit. Okay. In order to do this numerically, the first question was, since I know the integrable case, namely the Ablovitz-Ladik, and I have an explicit solution at hand, is there any way that I can say something about the non-integrable case? You can do that for the discrete nonlinear Schrödinger equation if you consider some sort of a generalized model that interpolates between those two ends. Namely, when g equals 0, you have the discrete nonlinear Schrödinger equation. If g equals 1, you get the integrable case, the Ablovitz-Ladik. So you're looking here not standing waves, but you're looking here periodic orbit. Okay. In order to do that, there are plenty of methods out there. You can think of the approach in terms of a Fourier series in time, okay, where omega is essentially connects with a period via 2 times pi over omega is my capital T, and my phi here are my Fourier modes that I'm going to consider in my ansatz. Okay, so however, you cannot do this from minus infinity to plus infinity. You cannot consider all those modes. You have to truncate this ansatz and consider a finite number of modes. Besides this, if you understand the stability of the solution that you're going to get, this time periodic solution, you just do exactly the same process. You perturb your fixed point, okay? Your Cn is your perturbation vector that whose evolution equations are coming from plugging this expression to your model, keeping terms of order epsilon, and that actually can tell you something about the stability. So in the context of this business, what you construct at the very end, you construct the so-called monodromy metrics. Its eigenvalues give you the Floquet multipliers, and that can tell you something about the stability of your solution. So this is actually a work that was in collaboration with my former undergraduate student, Jennifer Sullivan, where starting from the integrable case when g equals 1, okay, if you want to explore whether you can find solutions to the non-integrable case, you use pseudo arc length continuation method, and then you can start tracing branches of such solutions. But what happens is that for that value of omega, you have a turning point, you just cross again the integrable case, and then you keep crossing the integrable case again. Now, this is interesting from the following perspective. If I have an integrable model, and I have one solution, exact solution, this result tells people who work on integrable systems that there are more than one exact solutions in this problem that have to be found. So you give now some sort of an evidence numerically that such solutions should exist. And what happens is that in those solutions, starting from a flat background, those solutions that are far away from the integrable limit, this one has oscillations of the background. Those are called nanoptera in that context. And then when you cross g equals 1, this is now a numerically exact solution, but it must have an analog at the level of an explicit solution. Okay, so that is for a value of omega equals 5, And now, if you're brave enough, you can actually try to see whether you can, in fact, approach the non-integrable limit, essentially the model that is quite relevant in optics. And after doing this looping around the integrable limit, we were able to go all the way down to g equals 0, effectively getting this waveform, which is a novel solution to the discrete nonlinear Schrödinger equation emulating a Rogue wave. Okay? Now, in terms of the dynamics, those solutions, although they are unstable, I should have mentioned something about those insets, is that when you solve this monodromy matrix eigenvalue problem, you get eigenvalues that live on the unit circle, but when those eigenvalues, if you have eigenvalues that are off the unit circle, your solution is unstable with a positive real part. Okay, so all of them have essentially bands of unstable eigenvalues, but overall they are unstable. They're actually long-lived over 15 or 20 periods of time integration. So they have some likelihood to be observed in experiments in optics. Okay, 5 minutes. Okay, so the last one is a little bit. It's connected with the Rogue wave business, but the problems that I'm currently working on top of the Rogue waves and the matter waves in atomic physics models have to do with blow up. Specifically, if you pick again the nonlinear Schrödinger equation, but now with a power law nonlinearity, you have a parameter sigma here, and you solve the stability problem associated with this equation. First of all, the explicit solution is known in exact form, but if you study its stability, here is the spectrum of that solution. So you have essentially a real eigenvalue that actually comes off precisely at sigma equals to 2. And if you do the time integration of this solution, when sigma is greater than 2, in fact, the solution actually is going to blow up. Okay? So before moving exactly to what does it mean, it means that you have a solution that becomes unstable, so there has to be a bifurcation there, that something interesting is happening. Before moving to this, I want to make a statement and say that the NLS is associated, has two symmetries. One is that if psi is a solution, then the psi times e to the I theta is a solution. That means that the equation is U1 invariant, or it has a phase invariance. So that invariance is reflected in the spectrum by having two zero eigenvalues. Essentially, the eigenvector becomes the solution itself. It has two zero eigenvalues. On top of that, the NLS is invariant under space translations. So if you replace x with x plus delta, and you do your chain rule, the equation remains invariant. So this is an extra invariance whose eigenvector is essentially the derivative of the solution. That gives you another two zero eigenvalues. So what happens here essentially is that you have all along, you have 4 zero eigenvalues. There is one eigenvalue that comes from what we call as the band edge. It collides precisely at sigma equals to 2, and then it gives birth to this unstable eigenvalue. Okay? So what happens to this then when precisely that eigenvalue collides at the origin at sigma equals to 2? That means that if I have a zero eigenvalue there, that means that I have an extra symmetry in my problem, which allowed me now to rewrite the whole problem. Since I have those blow-up solutions, I can actually write my problem in a frame that actually co-explodes with the solution. So what does this mean? It means that I'm stretching space, I'm stretching my solution, I construct an equation in that co-exploding frame with G being how fast I blow up. When G equals 0, I have the solitary branch. And in order to solve this problem numerically, you can actually do a flow over this fictitious time tau. And in order to solve this, you have to include one extra condition to determine uniquely that value of G. Okay? So you do this by imposing an internal boundary condition, and that uniquely will converge asymptotically to a steady state, which is the blow-up solution to this NLS equation. Okay? So if you do this flow for the real and the imaginary part, when tau increases, then you approach to a stationary solution, that is a very good guess to do a bifurcation analysis over your parameter sigma. So you have now this initial guess that Newton's require. So when you do this bifurcation analysis, you get this bifurcation diagram. This is your solitary branch at sigma equals to 2 and beyond, the solitary solution becomes unstable. Then you have the emergence of two branches that kind of look like a pitchfork bifurcation, but in fact it's not, because a careful analysis of the normal form or the model that describes the bifurcation, if you have ever seen a pitchfork bifurcation, it has a cubic term. Here you have an e to the minus pi over the absolute value of g. So that's why you have this steep region. So it's not like a pitchfork bifurcation. It looks like that. It was quite interesting. And the two branches that you have here, one with positive g and the other one with negative g, are shown here. So that was quite interesting to see that this bifurcation is not a pitchfork, but it's similar to that. Okay, now we were able to track the point spectrum, meaning that all the eigenvalues that are very close to the origin and that are coming from the localized part of my solution, those eigenvalues, remember that for the NLS, we had 4 zero eigenvalues, and when sigma equals to 2, you have another 2 zero eigenvalues. So if you track all the 6 over sigma, we were able to do that. Of course, you have some undulations, which are coming from the finite size of the domain that you're using. But the careful inspection of the point spectrum is that for the value of sigma greater than 2, now those 2, 3, 4, all of those were precisely at the origin. When sigma is greater than 2, then you have the splitting of those modes. The U1 invariant mode, one of them stays there. This mode is coupled with that one, and those two are coming from that extra unstable mode that comes from that collision at sigma equals to 2. Well, I think I should summarize very briefly that I want to develop methods for studying nonlinear waves in the framework of atomic physics. Quite recently, I've had the great pleasure to be in France working with people who are using finite elements, and they have developed a package and toolboxes in the so-called FreeFM++. It's an open source software. It has lots of interesting tools. It is coupled with the PETSI library, the SLEPSI library, linear algebra libraries. It has mesh adaptivity. This is an ongoing effort that can be actually applied to collapsing waveforms. It's an ongoing direction for me. Recently, in fact, we did the work for the generalized KDV. Quite challenging problem because you have a solution, a self-similar solution. One part decays exponentially, the other one decays algebraically. It was quite interesting problems, and also use this technology to study multi-component Gross-Pitagoric equations in order to elucidate the configuration space of solutions of such interesting topics. So I think with that said, friends and collaborators, former students, and some references for you guys. Thank you.
Questions for Stathis?
Question from the
Zoom. How can I see?
Yeah, I think that's really.
So that is when you initialize the nonlinear product into the linear guess.
Yeah.
The linear guess doesn't have a size. So how do you determine the size?
The size?
Yes, the magnitude, the amplitude
of the eigenvector?
Yes.
So
in order
you mean
to initialize a nonlinear system, because it's arbitrary, right? The size of the.
well, you mean the Sturm-Lubin problem, right?
Yeah.
Oh, it's here. Oops. This one. Yeah. Well, yes, you have an arbitrary size because if C is an eigenvalue, then C times if C is an eigenvector, then C times C is an eigenvector. So that is kind of a trial and error because when you are very close to the linear limit, your mod C squared is very small, which means that the amplitude of that solution is going to.
But there's no systematic way to pick up a specific amplitude just to get. I mean,
essentially, you have a shape, And now you're playing,
You don't know the size of it.
you don't know the size, no.
But it's an easy parameter continuation there. I mean, you can try and error because it's just a one-dimensional branch.
In that case, okay, so there is a comment here because if you are trying to do this at the linear level and from that particular eigenmode, there are more than one solutions that are coming from that, it may actually become very sensitive. So you may start with an eigenvector or an eigenfunction in this context. When you initialize that, and you might actually converge to another solution.
Yeah, that's what,
I have seen this many times.
and that's what I was thinking, if there is a systematic way to pick up the amplitude in advance, not just try and error.
There is something that I have done, and it has been working so far, is that you can actually have a solution that it is, let's say, of order 10 to the minus 1, the amplitude, okay? And you're not very close to the bifurcation point, so you're quite far. So there is no other way the Newton's method should converge to that solution, especially in such type of problems where you have an external potential and thus you have an attractor there. So it has to converge. But I have seen it, how sensitive this can be. Yeah, absolutely. Yeah.
We talked about these periodic soliton solutions and
Yeah.
looking at the limit as the
Yeah.
period gets really long. Is this just a numerical technique, or is this something that might actually apply to a physical system?
Oh, this is actually a numerical technique in the more general context of finding periodic orbits. So if you want to find, let's say, a solution psi of t such that psi of t equals to so now what you're requesting is that I want to find a solution for a capital T such that this is true. There are techniques that essentially describe the same setup as a boundary value problem with periodic boundary conditions, where capital T is your your period or the length of the domain in time that you use. But this is essentially a numerical technique that bypasses this boundary value problem business. But the advantage that you have here is that you know the period, or you prescribe the period from the get-go, and you're requesting whether the associated root finding problem has a solution for this capital T. This can be applied to not only this setting, but many other settings. As soon as you know the period. If you don't know the period, then that becomes tricky for the following reason, because most of the models that we have are time translation invariant, meaning that if I do a shift in time, if t becomes t plus delta, same thing, my equation is going to be invariant, which means that I won't be able to converge uniquely in one solution because I have this invariance. In order to bypass this, you have to add an algebraic condition, some sort of orthogonality condition, that you penalize the system in order to get one solution out of the group orbit of time translations.
But in essence, what you're doing is Newton on a stroboscopic.
In this case, I just have essentially the form of the solution that I'm looking for as a Fourier series in time, and what I'm looking for is just what are the Fourier coefficients. Yeah, that's one way. But here you know the period. If you don't know the period, it's tricky. It's a very open research direction that how to do this systematically. There are many orthogonality or penalization methods to do that. Some work very well, some others they do not. In some other cases, they work well. Yeah.
All right, so let's thank Stathis. Thank you, Stathis.
Thank you. Thank you very much.
And we are all invited to join us for a beer at Trujillo's. So we're not going to Eureka, but we're going to cross the road in Trujillo.